hello and welcome. In this video, I'll be covering section 3.2, which is over extrema and the first derivative test. My goal for you by the end of the video is to be able to recognize the occurrence of relative extrema of functions, to be able to use the first derivative test to find the relative extrema of functions, and to be able to find absolute extrema of continuous functions that are on a closed interval. So let's go ahead and recap what relative extrema are. Remember, extrema is kind of the plural of extremum. So down here near the bottom, see extremum, that would be the singular version. Extrema is the plural. Not that that's a huge deal. But extrema, if you recall, usually we use the words like maximum or minimum in our description. That's just kind of the collection together of all of the max and mins we just call extrema. But anyway, so with this, notice the definition, and we have to basically allow f to be some function that actually is defined at the value c. And so the y value at that c value for the function, or f of c, we would be able to say is a relative maximum if every single other y value around it inside of some small interval from a to b that has c. So notice c would have to be between those two values. So if I go to the left and to the right of whatever that c value is, if the y values around it get smaller, then that means it must be a high point for the graph in that small portion of it. Hence the name relative. It's just the maximum in relation to all of the points around it. Conversely, we could think the exact opposite. If all of the other y values around that function were higher than the function's value at c, then at that point that must be a low point for the graph, or a relative minimum. So again, what's kind of nice about this is if we know that the function has an extremum at that value, in other words, whether it's a maximum or a minimum, one thing that we can say is it will occur at just that x equals c value. So that would be more like the location. If I wanted the value of the maximum or minimum, that would actually be where I would use the y value. So at the end here, notice how can we identify some of these things. This is more where we're going to get the ability to identify the relative extrema, is they always will happen at what we call critical numbers. So if you think back to last video, the critical numbers are always whenever the derivative equals 0 or is undefined. So if I have the f prime of c equaling 0 or the f prime of c being undefined, that must be a place where there's some relative extrema happening. So what we'll do to actually identify those things is do what's called the first derivative tests. So again, at the top here has kind of here's all the definition, or not necessarily the definition, but here are all the circumstances we need to have. So f does have to be continuous, and on this interval it's just saying that between the a and b values, c is the only critical number that we have. So we're just shortening up maybe the entire domain to just a smaller portion of it, where c is the critical number on that small area of the graph. If f is differentiable, except possibly at c, in other words, it could be a sharp edge at that c value, we can classify that either as a relative maximum, a relative minimum, or it might not be either of those. So it's not always a guarantee that just because it's a critical number it has to be a high point. It could be a different kind of point that we'll talk about actually in a future lesson that's called a point of inflection, potentially. But we're not really focused on that quite yet. We're just identifying the extrema. So in order for the, first derivative test to be applied, all of that has to be true. And what we will do is essentially just kind of set up our sign line. And if we notice that the derivative is negative to the left of that value and the derivative is now positive to the right of it, so it would be similar to us doing the increasing decreasing idea. If we notice that that switch happens, if it's negative on the left, positive on the right, then at that point we can say that must be a relative minimum. Conversely, if it was positive on the left and negative on the right, then that must be a relative maximum. So notice it just became its exact opposite statement between saying whether it was a relative minimum or a relative maximum. Now, if it ends up having the exact same sign on both sides, meaning it's negative on both sides of c or it's positive on both sides of c, then at that point we can say that it's not going to be a relative extremum, but it potentially could be a different kind of point that, again, we'll talk about at a future video. So maybe to simplify that a little bit for us, because that was obviously a lot of weird and nerdy writing there, essentially if you see that you have a function switch from decreasing to increasing, So that would be like if I were to draw a little sketch of a visual. If it was coming down the page and then all of a sudden it switched and it started coming up the page, notice that would have to create what we would consider a low point for that part of the graph. Hence why we would know that that is a relative minimum. And if we had the exact opposite happening, saying it was increasing coming up the page, but then it switches to now decreasing, that point now must be a relative maximum or a high point for that small part of the graph. And again, if it doesn't switch from increasing to decreasing or vice versa, at some critical number that we've identified, then at that point we can't really say anything about it being a part of this extrema, or it singularly is not a relative extremum. So now that we got all that long-winded explanation of what's going on here, hopefully we can simplify this with some of the examples and start to understand what's going on. So for this question, notice all it says is to identify all of the relative extrema of that function. So to come up with our relative extrema, we'll just use the first derivative test, which basically means we need the first derivative. So if I go ahead and figure out f prime of x, it looks like this one's just going to be a few power rules. So 2x cubed, that's going to just turn into a 6x squared, plus the 9x squared, that would turn into 18x, and then minus 60, and then the plus 10 should turn into 0. So at this point, we would just look at it and see if we can potentially factor it and identify where that equals 0. So it looks like with this one, 6 goes into all of those, so we can make the quadratic a little bit more manageable. So if I divide the 6 out, that will give me x squared on the first term, plus 3x in the middle, it looks like, and then minus 10 at the end. And again, critical numbers happen when it's either 0 or undefined. This is never undefined, so I won't have to worry about that, but I can solve for when it equals 0. With this quadratic, I could just say I'm going to divide the 6 over, so I don't need to worry about the 6, I just need the quadratic. So the parentheses that would turn into, I'd want to multiply to negative 10 and add to 3, so that would be a positive 5 and a negative 2. So x plus 5, x minus 2. Set that equal to 0, because again, that coefficient of 6 that's in front, if I divided both sides by 6, it would just disappear anyway. It's just when the parentheses that equal 0 that I would end up getting those, or the derivative to be equal to 0. So it looks like my two critical numbers in this case are going to be negative 5 and positive 2. So what we can do is go ahead and set up a sign line using those values, negative 2 and positive 5. We can really just identify where the increasing and decreasing is happening. That's going to be more what the useful part of this is. So if I go ahead and pick some numbers on each of these intervals, I'll go ahead and test to the left of negative 5, maybe a number like negative 10. For the middle interval, I'll use 0 as my test value, and above 2, I think positive 10 should be safe. And I'm just going to use the two parentheses that I have, the factored form of my my derivative here, even though there technically is a 6 right here, that 6 being positive. All I'm looking for is my answer going to come back positive or negative anyway, so that 6 really is not going to change a whole lot. So if I plug in a number like negative 10, it looks like the first parenthesis would come back negative, the second parenthesis would come back negative, but two negatives when I multiply would come back positive. If I do a similar thing with 0, the first parenthesis is positive, the second parenthesis is negative, a positive times a negative would come back negative. And a number like positive 10 should make both parentheses, yes, in fact it does make both of them positive, and two positives when I multiply would stay positive. So I then know that this part of the interval, or that interval right there, is where it would be increasing. I know the middle one is where it would be decreasing. And I know the last one is it switches back to increasing. So again, the simplified version of the first derivative test here basically says if I switch from increasing to decreasing, that value at negative 5, I could then say, well, that's going to be a place where it must have been coming up the page and then started coming back down the page. So that would be what we would call a relative max at that value. At 2, on the other hand, it's actually decreasing coming into it and then comes back out as an increasing, so that would be coming down the page and then switch by coming back up the page. So I could then say, well, that one must be a relative minimum. So those are the, I guess, places where it happens. Those are the x values. How would I get the y values? Well, remember, y values always come from the original, so I really would just need to figure out what is the function at negative 5, and then what is the function at positive 2, and see if we can do that relatively fast. I'm going to go ahead and bring a calculator into this process here for negative 5. So I'd have 5 times negative 2 times negative 5 cubed. Then I'll follow that up with adding 9 times negative 5 squared, then minus 60 times negative 5, and then plus a 10. And it looks like that's going to come back as 285. I do a similar thing with 2. So it would be 2 times 2 cubed. Go ahead and add that with 9 times 2 squared. Take away 60 times 2, then add 10 to that result. That comes back as negative 58. So I can then, at the end here, go ahead and say identify what those points were. Well, we had a relative max that we've identified because of the switch from increasing to decreasing. That must be at that negative 5, comma 285. And then we have our relative min, or minimum. That would be at that point 2, comma negative 58. And as you can see, I included a little, at least, picture of the graph here so we can kind of look at what the location is. So the axes are definitely counting by completely different values. Notice I've got negative 10 and positive 10 on the x-axis, but I've already got negative 500 and positive 500 on the y-axis. So that was just to try and make it such that it fit on the particular grid. But each of those points, if we look at their location being at negative 5 and then all the way up at 285, does make sense for this first point right here. And then the second point being at positive 2 and then down at only negative 58, looking at the scale, that also seems reasonable. So sometimes you can use a calculator to your advantage, or Desmos, or whatever you have at your disposal, just to make sure that the graph kind of matches what your final conclusion is as far as identifying your extrema. If you end up saying that your maximum was somewhere in the positive area, but you look over in the positive and it's actually a low point, you might go back and just double check your math and make sure that you are plugging numbers in either correctly or that you even have the correct critical numbers. Let's go ahead and move on to another example here. Hopefully I can work through this one a little bit faster than the one before. But again, notice the instructions are just saying to identify the relative extrema for a function. So we're going to apply the first derivative test. So starting with identifying our first derivatives, pretty key start. So this one, it would be 4x cubed, then minus 3 times 2, 6x squared. And again, I just need to find the critical numbers, so set that equal to 0. Looks like I can factor that, so 2x squared can come out. That would leave a 2x and then a minus 3. So if I set each of those equal to 0, the first one, it looks like it would just be 0 as my solution, because if 0 was being squared, then doubled, it still would make the whole thing 0. Second one, I would add 3 divided by 2, so positive 3 halves. So let's go ahead and set up our sign line to do our increasing and decreasing, the key part of the first derivative test. And I'll just pick some numbers that are on each of these intervals. So negative 5 I think would be safe to the left of 0. Positive 1 in between there. There's not many other nice numbers. And then maybe positive 5 on the end. So really I'm just going to plug into my factored version right here. And if we think about it, the 2x squared, no matter what, when you square it comes back positive. So I really don't need to worry about this outside part. It really is just going to come down to what happens when I plug in there. So when I plug in negative 5, I'd get negative 10 take away 3. That would come back negative. If I plug in 1, I'd get 2 take away 3. That goes negative as well. So that basically means at 0, we can tell that since it did not switch from decreasing to increasing, I can't really say anything about that. That's not going to be a relative extremum. If I go on to the last one, check with number 5. 5 doubled would be 10, take away 3, that would be positive. Now that one did switch, so I can then say, okay, at 3 halves, it went from decreasing to increasing. So that means it must have been coming down the page followed by coming up the page, so that must be a relative minimum. So to come up with or identify our ordered pair, we've now got the x-coordinate that we can identify as 3 halves. Our y-coordinate is something I would have to do just by plugging it in to the function, because remember all of the y's always come from the original. So this one would be 3 halves to the 4th power, then take away 2 times 3 halves cubed. And so we could go ahead and simplify this. This would turn into 81 over 16. Take away 3 cubed is 27, doubled is 54, over 2 cubed, which is 8, so it looks like I just have to double both of those numbers, so that would be 81, take away 108 over 16, which what would that turn into? 27/16, but negative, so negative 27/16 would be our y-coordinate. And as you can see with our sketch over here, that point down on the bottom right being positive 3/2 over, it looks like about 1.5, yes, according to the grid. And then down negative 27/16, so that would just be a little bit less than 2. That seems reasonable with my grid as well. And then the fact that at 0 itself, so notice at the origin, when it was x equaling 0, it really was not a low point or a high point, hence why when we tested using the first derivative test at 0, we weren't able to make any sort of conclusion about that being an extrema. It just kind of flattened out for a second and then continued on down, so it was not truly a low point or a high point at all. And we'll go ahead and try another example, something that's a little bit more funky. You can kind of see the graph in the bottom right corner here. But with this one, we're going to go ahead and just start the same way we have with the other two, figure out our first derivative, so f prime of x. With this one, I'd have 2/3 multiplying with 6, so 6 divided by 3 would be 2, times 2 would be 4, x to the negative 1/3 when I subtract 1 from that exponent, then minus 4. So it looks like I should be able to kind of move that negative power to the bottom and say that this is really a 4 over an x to the 1/3, then minus 4, which I could say is over a 1. So I could now start trying to make this one single fraction by multiplying by x to the 1/3. And that would give me a common denominator now that I could say is all over x to the 1/3. And it looks like the numerator would now have 4 minus 4x to the 1/3, which I could probably factor a 4 out of that, but we'll worry about that when we actually do this next step, which is set equal to 0. So remember, our critical numbers are going to be whenever the top and the bottom equal 0, because I want not only the values where it's 0, but also when it's undefined. So let's go ahead and just identify our critical numbers. Start with the easy one, which is when is it undefined. With this one, it would just be when the bottom is 0. So one of my critical numbers is going to be 0 itself. Then the other part is going to be when the top equals 0. So if I maybe off to the side, do it down here in the bottom right. If I go ahead and factor that 4 out, that would give me 1 minus x to the 1/3. Again, if I set that equal to 0, dividing by 4 would cancel that. So I really just need to solve when is 1 minus x to the 1/3 equal to 0. I could subtract 1, get negative x to the 1/3 equals negative 1. Divide by negative 1. I've run out of room already. Did not use very good spatial reasoning there. And that would give me positive 1. And to cancel a power of 1/3, I would just cube both sides. And we'd see that x would just equal 1. So my two critical numbers are just 0 and 1. Probably could have figured that out, that the only number I could subtract from 1 would be 1 itself to equal 0. So we could have maybe done a little mental math with that with this part right here. But anyway, we saw all the steps. There we go. So now we can go ahead and set up a sign line. 0 comes before 1, so we'll go ahead and set it up that way. And go ahead and start plugging in some numbers. So if I go ahead and maybe choose like negative 5, actually, let's see, what is an easy number to do a cube root with? Let's do maybe negative 8. Something between 0 and 1, that would be like 1/8. And something greater than 1, positive 8. Reason again I'm choosing 8s is because 1/3 power is really a cube root. So cube root of 8 is 2. That's a nice easy number to kind of utilize for our formula here. So let's go ahead and try and figure out, do I get positive results or negative results for each one of these? I'll just go what happens on top and then what happens on the bottom. So if I did the cube root of negative 8, that would come out as negative 2. So it'd have 4 minus 4 times negative 2, so that would turn into 4 plus 8, which is positive on top. And then over the cube root of a negative, that would be a negative. So positive over a negative, this interval would be a negative or a decreasing interval. If I try 1/8, cube root of 1/8 would be 1/2. 1/2 times 4 would be 2. 4 take away 2, that would stay positive on top. And then on the bottom, the cube root of a positive is positive as well, so a positive divided by a positive should be positive, so that means it must be increasing there. And then plug in positive 8 this time. That would be the cube root of positive 8 is 2. 4 times 2 would be 8, so 4 take away 8 on top, that would come back negative. Whereas on the bottom, I would have the cube root of positive 8, that would actually turn into a positive value. So I have a negative divided by a positive, which is negative. So that must be a decreasing interval. Not sure why I put the negative above this time. So it's negative, which means it's decreasing. So what can I say about these 2 points? Well, at 0, it was decreasing coming in, then increasing coming out, so that must be a relative minimum. And at positive 1, it was increasing coming in, but then switched to decreasing coming out, so that must be a relative maximum. So to be able to come up with each of these, I just need to plug the values in. I'm going to go ahead and just start setting up my final answer here. My relative minimum has an x-coordinate of 0 that I know for sure, and our relative maximum has a value of, or an x value of 1, and I just need to plug in. So this one should be pretty easy to plug into. 0, when I plug it into the original, just gives me 0 take away 0, which is 0. 1, when I plug it in, it's going to be also pretty easy. That would just give me 6 take away 4, which would be 2. So as we can see from our picture here, having a relative minimum at the origin seems reasonable. It's kind of a sharp edge, hence why the derivative was undefined there. And then the relative max being at 1, 2 looks reasonable with that graph as well. So it seems as though we are doing okay. So hopefully those practice problems there have helped solidify what the first derivative test is, as well as identifying relative extrema. So let's go ahead and move on to what we call absolute extrema. So if we have a graph that has a closed interval, essentially remember what that means is I would have endpoints. In other words, I wouldn't have arrows at the end. So every single time when you have a closed interval, there should be an absolute true highest point and an absolute true lowest point. But what an absolute extrema is, or extremum is, in singular sense, is if it's the lowest point out of every single I guess y value of your graph on some given interval I, then at that point you can say it's the absolute minimum of that interval. Same thing if you had every single point be, or if that point happened to be the highest out of every single point, then I could say it's our absolute maximum, so long as it's on that closed interval and it's every single x that you plug in. In other words, every y value you get back out. If they happen to be lower than the f of c, then it's a max. If they all happen to be higher, then f of c must be a min. So on occasion, instead of saying absolute maximum or absolute minimum, sometimes we can just say the minimum of the graph or the function on the interval or the maximum of the function on the interval. So again, as I was talking about, if I have a closed interval, so in other words, we don't have any arrows, it doesn't go on to infinity or negative infinity, at that point we can say if it's truly closed and it's continuous, meaning there's no gaps and there's no asymptotes, then at that point we know there has to be a true minimum value as well as a true maximum value. So how would I find them? Well, essentially what we would do is figure out what the critical numbers are and just evaluate the function at those critical numbers, and then also plug in the endpoints. So keep in mind the endpoints actually could still potentially be the true highest point or the true lowest point. So I would just plug in those numbers as well, and then I just compare all of the numbers. Whatever came back the smallest, that's what we're going to call the minimum, and whatever comes back the greatest is what we're going to call the maximum. So let's go ahead and try an example of this just to kind of give you a visual of what's going on. We could probably picture what this graph is. It's just a quadratic, so this is going to be a U shape up because the a value is positive, and it's over this interval from 0 to 7. So notice it's not the entire parabola or not the entire quadratic function. It's just a small snippet of it that starts at 0, stops at 7, so it cuts those arrows off. So what we'll do is figure out our critical numbers first. So for this one, it would just be find the first derivative, which is just 2x minus 8. and then I set that equal to 0 or any undefined value. Well, it's never undefined, so I don't have to worry about that. So this would just turn into, when does 2x equal positive 8? Because I would add 8 over and then divide by 2. So critical number I got in this case is going to be 4. So now I just evaluate what is the function at 4. So that would just turn into 4 squared, which is 16, minus 8 times 4, which is 32. Then add 10 to it, so that would be 16 take away 32 is negative 16 plus 10. That would give me negative 6. Then I'll plug in now the endpoints. So f of 0, in this case that would just be 0 take away 0 plus 10, so that would come back 10. And then whatever the function is at 7. So this one would be 7 squared 49 minus 8 times 7, so that would be 56. And then plus 10. So 49, if I take away 56, would go to negative 7, plus 10 would give me positive 3. So now I just look at which number is the largest and which number is the smallest. Well, if we look at what we got here, the smallest would have been the negative values, so I know that I have an absolute minimum that would be at that point 4 comma negative 6. And I have an absolute maximum on this closed interval. Looks like when 10 happens, right? So this was the smallest. This one was the greatest. So I can then say the absolute maximum for this one would be at 0 comma 10. The other endpoint, 7 comma 3, is not the true highest point, but it's also not the true lowest point, so it's just not a part of our answer set, because all this really wanted was the minimum and the maximum value. The fact that 7 comma 3 wasn't either of those doesn't matter. We just only needed to identify those 2 key points. I guess it will be important to note that if you ever do plug in and say you get the exact same number, so let's say 2 of those would have come back as 10, then you would actually say both of them are the absolute max values for that particular function. So hopefully this video has been helpful. Again, we were identifying our relative extrema using the first derivative test. We were finding our absolute extrema on a closed interval, and then just utilizing the increasing, decreasing, and where the critical numbers are where they switch to be able to identify pretty much all of these things. So notice the first derivative was pretty much as far as we had to go, and it was just a lot of setting equal to 0 or setting it equal to whenever it's undefined. But anyway, appreciate you taking the time watching this video. As always, if you have questions, just reach out and let me know, and I'll do what I can to help. I guess I'll check you next time.